Thanks to the organizers for allowing us to present this work. This is actually this work is the master thesis of my former student Andres Lopez.
Dario, something is wrong. At least my. Can you share the desktop, not the presentation slides? Oh, sorry. Okay. Yeah.
Okay, and this work is in collaboration with also with Hugo and Karani. So during the last year, we performed. We developed a spectral method named Generalized Sturmian Functions, and this method was implemented to study the structure and the scattering process of atomic systems. The method uses complete an orthogonal basis set of generalized Sturmian functions, which has the appropriate boundary conditions. We started with negative energy functions to study bound states using simple cases, to put the method on solid grounds to study convergence issues and the integrals involved, the adequate choice of optimal parameters and other numerical aspects. All this was summarized in the first MEST meeting in Turkey. This is a long paper, and Philip should know that because he did a wonderful work in the edition. Now, after this work, after the bound state, the GSF approach was rapidly implemented for continuous states. And here is where the good properties of positive energy Sturmian function, generalized Sturmian function, demonstrate the power of the method. In this work, the objective is to develop and to implement general Sturmian function method in prolate spheroidal coordinates. We want to move to molecules. And the development will follow a path similar to the one adapted for atomic case. We will first consider bound one-electron molecules. Then we will move to the continuum part of the spectrum. And by studying benchmark one-electron molecular ions, we will wish to validate the new computational procedure, the codes. We wish to check thoroughly all the conversions and precision issues. And so we will start with the most simple case. We will do benchmark calculations as simple as we can. We will assume a fixed nuclei approximation, Born-Oppenheimer. We will neglect relativistic effects, nuclei finite mass effects, quantum electrodynamics, all the interesting features we saw yesterday. We are not talk about that. These are the prolate spheroidal coordinates. There are, if you see here, the zeta constant curves are stretched spheroids, and the eta constant curves are hyperboloids. We need to rotate this curve along, this is for a fixed phi angle, azimuthal angle, so we need to rotate that along the z-axis in order to obtain the revolution surfaces of zeta constant or eta constant. And the Hamiltonian in this coordinate system is this one. And it's very nice because it's separable. So you can express the solution as a product of three functions. The corresponding equations are those. The azimuthal function is easily separated, exactly as in the hydrogen atomic case. For simplicity, we will assume here, from here to the end of the talk, that m is equal to 0. It's not any problem. And upon elimination of the azimuthal dependence, we obtain the following angular or quasi-angular and quasi-radial equations. They are coupled equations through the energy, and there is another coupling constant A. In order to implement the generalized Sturmian function, we need to define the Sturmian equation, and for the angular equation, we define this. The reason of this is that they are Legendre. These are the equations that generate the Legendre polynomial, and we also know all the properties and the eigenvalues, etc. Of course, these are the first 9 Sturmian basis elements, the angular elements. Okay. And for the radial equation, we choose this Sturmian equation. And here we have a generating potential. And here we have the Sturmian energy. These are free. This is something that we choose. So we can put here the energy we want. It's not the actual energy of the state. And this is a potential that can be any potential. The only condition is that it must be a short-range potential. And here are the 9 first radial basis elements that we use in our Sturmian calculation. And we propose here 2 different methods to solve the coupled differential equation. In the first one, we solve alternately the angular and the radial equation. We expand the solutions, the angular solutions in n angular Sturmians, the radial solution in m radial Sturmians. And with this expansion, together with the Sturmian equation, we can replace, for example, this part very easily, and we obtain the equation, this equation. This, we take this equation, multiply from the left by another Sturmian, we integrate over the angular domain, and as we obtain an generalized eigenvalues equation. So assuming a given energy value, P, the angular part reduced to solving the generalized eigenvalue problem, solving the eigenvalues A. This is the separation constant. And the eigenvectors, C. The eigenvectors are the coefficients of the expansion. It is important to note that all the matrices are calculated only once at the first iteration. We don't have to calculate that for any iteration step. Another advantage is that all the matrices can be evaluated analytically using known properties of the Legendre polynomial. Once the A eigenvalue is obtained from the angular equation, we make a similar procedure to the radial equation. With the basis expansion, with this basis expansion, and with the Sturmian equation, we put all this in the radial equation, and we obtain this equation. Again, we multiply from the left by Sturmian, we integrate over the domain. Now the domain is from 1 to infinity, and we obtain another generalized eigenvalues equation, and now these eigenvalues are the energies. So we know that because we choose this energy, and we obtain the energy of the state. Again, the matrices are calculated only once at the first iteration. We don't have to calculate and to solve anything in the iterative process. So in summary, this method works like that. We solve alternately the one-dimensional angular equation. We assume a fixed energy here, and with this energy, we obtain the separation constant A. Then we use this constant A as a fixed value here, and we solve the one-dimensional radial equation, and we obtain the energy. We took this energy and we put here, and we start again. We repeat this procedure until convergence is achieved. Let me show some results. We took the energy value given by Scott, and with this value we put here, we solve this eigenvalue, we solve the separation constant, and with only 4 bases, the benchmark value of Scott is reached with only just 4 elements in our basis. In contrast to the angular part, the approach here for the radial equation is completely numerical. I don't want to provide the technical details here, just I would say that we use a kind of predictor corrected algorithm. And one point is important: in order to solve this equation appropriately, the crucial aspect resides in the fulfillment of the boundary conditions at the origin. We endorse this conclusion trying to solve the radial equation with other methods and using different mathematical softwares, and obtaining very different results for different numerical grids. We even try to solve this equation fixing the energy, but we obtain this converged solution yield eigenvalues too far from the correct value. And now, these are our results. You see here 2 different energies. The difference in these 2 columns is the initial Sturmian energy. In this case, we start with -1 atomic unit, and we obtain this value. With only 9 bases, 9 elementary bases. It's very small bases. Now, if we use this energy as an initial starting point, we have 6 figures, 6 significant figures of agreement with beyond. This is a very large calculation. Having solved the matrix equation, the eigenvectors give the coefficients that allow us to construct the ground state angular solution, the same for the radial solution. And the product of these 2 solutions gives the total solution, the total ground state solution. And it's best visualizing by converting the prolates into Cartesian. And of course, you must rotate this figure along the z-axis in order to obtain the full. This is just for one particular azimuthal angle. We repeat this calculation for different internuclear distance. We can choose this parameter for any one of the distance, but we don't need to do that. We can use R equal 2 atomic units here, and then calculate the total energy for different internuclear distances. The equilibrium, bond length, and the corresponding energy are in agreement with the best value given in the literature. We challenge also our computation method considering very small internuclear distance. In general, arise many instabilities and errors, so it's a challenging calculation. And the ground state evolves from a molecular to an atomic shape, and you can see here we have even the Kato conditions. So, and the energies, of course, should go towards the helium plus, and this is what we obtain. We can also calculated excited levels. And again, this is the energy we start here with the ground state energy. And anyway, we obtain a good energy. When we start with that, in only 4 iteration steps, we obtain the benchmark energy given by Scott. We use only 3 angular bases and 6 radial bases. This is 18 elements in our basis set. It's very small. For other excited labels, our iterative method compared very well, very favorable. Here are the angular solutions, the radial solutions, and when we combine that, we obtain this excited state, this one, the next one, and the next one. And here is a summary of the energies. And we are in very good agreement. The calculation of Bian used 20 angular splines, B-splines of order 7, and 80 radial B-splines. So it's much larger than our calculation. We also calculate other asymmetry heteronuclear molecular ions, the helium hydride and the lithium hydride molecular ion. In order to compare with the literature, we use a fixed distance of 4 atomic units, and this is what we obtain. This is the ground state wave function. The distribution of the electron density is clear asymmetric, shifted toward the nucleus with the larger charge, and the shape acquires more an atomic-like form centered on the heavy nucleus, and of course this is more evident for the lithium hydride. We can show the efficiency of our method, and again, we are comparing with large calculation. The Campos calculation has 22 angular and 22 radial elements, so we are in good shape. As a summary of this method, I can say the advantage of the method is that we have 2 separate equations, but they are one-dimensional, so that reduces significantly the computational cost. The principal part of the equation, it means the derivative, are already dealt with the basis function, so we don't have to do calculations to solve the differential equation at any iteration. Okay? The basis set has that already solved. There is a drawback that each molecular state requires a new basis set. That means that from all the eigenvalues A and P resulting from the calculation, we must select only those corresponding to the eigenvectors having the right number of nodes. For each molecular state, different iterative procedure is thus needed. It's not a big problem, but anyway, we develop another method because we wish to exploit the full advantage of the spectral method, which allows one to obtain many states on one shot. The direct diagonalization of a 2D Hamiltonian is generally very costly from the computational point of view. Within the finite difference framework, the Hamiltonian matrix becomes huge and is intractable. Now, spectral method can reduce significantly the matrix size to diagonalize, but computationally still represent a hard task. Within our generalized Sturmian function method, the size of the matrices are reduced even more. They are very small matrices. This is because the appropriate physical behavior is explicitly introduced in the basis set. So the idea, let's see how it works. We construct a 2-dimensional Sturmian basis set, which is the product of the angular and the radial Sturmian defined previously with these equations. And we took the Hamiltonian, we replace by the Sturmian expansion, and since this part, the big part of this equation is already solved in the basis, we obtain this equation. Okay. Again, we need to project from the left, but now we project with the two-dimensional Gaussian, and we obtain again a generalized eigenvalues equation. Now, it seems that the integral are two-dimensional integrals, that this is difficult, but in fact, all the integrals are completely separable. For example, take a look at the first integral. We have here from the left a two-dimensional Sturmian, in the right another two-dimensional Sturmian, but there is nothing that couple the two variables, so it's just a product of two integrals. And with only one diagonalization of these 18 basis functions, we obtain energy, this table. The energy of the Sturmian was minus 0.2 atomic units. It's clearly different from the ground state. And this is a compromise that leads to a good precision for the whole set of labels presented here. If one wishes to improve the energy accuracy for one particular state, can choose a different Sturmian energy closer to this state, and it's not as I say, it's not an expensive calculation, so you can do that very easy. In conclusions, we have a method that produces excellent results for bound states in atomic systems, and we demonstrate that this method is best suited for scattering calculation. We did a lot of work. I will show now because the time is short. And then in this work, we extend the method to work in spherical Prolate coordinates. We developed two methods. One is the iterative 1D method, in which the angular and radial equations are solved alternately, fixing the energy and the coupling parameter, in each case. With this method, we obtain accurate results for bound state of the hydrogen molecular ion, for ground and for excited labels. We obtain accurate results for other diatomic heteronuclear molecular ions like helium hydride ion or lithium hydride ion. Then we develop a two-dimensional method in which we directly diagonalize the Hamiltonian. We have very good agreement. And the advantage is that we can obtain many labels in one single calculation. Both methods are time-wise computationally efficient. The main reason is that first, we work in the natural coordinate system. We don't have to do derivatives. This is for the first method, the iterative method. We don't have to do derivative or to solve the differential equation at any step. We can do that once, construct the basis, and from this basis, we use this basis, and that works in this way. And finally, these are the intrinsic properties of the generalized Sturmian function, that we can construct the basis as to obey the appropriate physical boundary conditions. Okay, that's all the talk. Thank you very much.
Now I can unmute. Okay, thank you very much for interesting talk and especially for perfect timing. And we have time for questions and comments.
I would have a comments if there are no comments from other speakers.
Yeah, Krzysztof, go ahead.
Thank you, Irek. So I would say that there are many other methods which are very efficient for H2 plus system. Let me mention the one which has been applied by physicists to Slater. I mean, the functions with pure exponentials. And with these functions, one is getting 30, 40 digit precision. So I would say there are many approaches, and especially the one which is used by physicists relies on pure exponential, maybe with some complex values of exponents if we are considering the high excited states. And there is also, one should mention that such a system like H2 plus or HD plus are measured very accurately. Even recently, there were several papers in Nature and Science, in fact, 2 papers in Nature and Science, about very accurate measurement of transitions, vibration and rotation transition in HD plus. These measurements allow for the determination of the proton mass. These were so accurate that from these measurements we obtained the most accurate value for the proton mass. So such a system are used in practice for the definition of fundamental constants. Certainly, one has to go beyond the Born-Oppenheimer approximation, but it's not a problem because it's a 3-body system, and 3-body system can be calculated with arbitrary precision, even with using such a simple function like pure exponentials. Thank you.
Thank you for the comment. Dario, you want to say something? Or?
No, it's I agree. But again, we must start with something. The way to do this calculation is very. We are interested in scattering calculations, so we cannot go directly to scattering calculation. We need first to understand the method and to do very simple calculation. This is the reason we are not taking finite mass effects or relativistic effect. Nothing. It's just the most simple Hamiltonian we can, and use these benchmark solutions to check how we are performing. But yes, we agree that there are many very interesting calculations doing in the last time by this group.
Okay, thank you. Any more questions or comments? Okay, I don't see, so we can move on to the next speaker. Thank you, Dario.